Section 6.1, slope fields. So when you look at this picture, what do you see? Well, you see probably lots of little dashed lines. Do you see anything kind of hiding in the picture? What do you notice? It looks like we have a family of parabolas, and those parabolas could be anywhere depending on what the y-intercept is. These are tangent lines. And if I take, say, a point right here, and this is concave up, so my tangent lines need to lie below the curve. So this curve would come through maybe like about that. Okay, and then I would go to the other side and do the same thing. Something like that. Well, this is called a slope field. It is a field of slopes. So this is the slope field for the derivative equation dy dx equals x on the intervals from -2 to 2 for x, -2 to 2 for y. But we know how to find what the equation of the parabola in the curves here would be simply by antidifferentiating that function. Antiderivative of 1 dy is y. Antiderivative of this is 1/2 x squared plus some constant c, where I could be anywhere on that function. Again, if we look at this slope field here, you can see I've drawn in one little curve and another little curve through some initial points, but you can see this looks like it might be an exponential type slope field. This is the derivative equation dy dx equals y on the interval from -4 to 4. So we know how to separate our variables and antidifferentiate this. This gives me ln of absolute y equals x plus c. Well, that's interesting. I will tell you that we have something coming up because remember, log is exponent, right? So here's some foreshadowing for section 6.3. Since a logarithm is an exponent, then this is my exponent on the base of e. Okay, and if we think a little more, we can recognize that e to the x plus c1 is e to the x times e to the c1. Remember, when we add our exponents, we were multiplying. And we can do more with that. So, in fact, this is exponential. What does this one look like? In this slope field, I could, depending on where my initial point is, I could be looking at horizontal hyperbolas or vertical hyperbolas. Again, this has a differential equation that looks like this. We are on the interval from -4 to 4 and -4 to 4. Again, we can do something called separate our variables. Integrate both sides, y squared over 2, x squared over 2, plus some constant, plus another constant. Notice that we get our, with the algebra, there's our hyperbola form. We have a lot of unknown constants. We'll collapse them together to one unknown constant. And here we have what could be one of our versions of the equation. And notice, if I were looking at this as my equation of my hyperbola, taking the derivative is going to require implicit differentiation. So you actually know a lot of things without realizing what you know. Here's another neat slope field. This kind of looks like a contour field or something that you might see when you're hiking with a map, looking at elevation or maybe looking at wind patterns on the weather. Okay. The derivative for this is this here. We won't work on solving this one. But this brings us to the topic of slope fields. It's not always possible to solve most differential equations explicitly. However, it is still possible to get a sense of the solution of a differential equation through a graphical approach using the slope field or a direction field formed by substituting x and y into the differential equation. This forms small pieces of tangent lines at each point, and you get a feel for the behavior of the solution curve that's hiding in between all those little tangent lines. And if you do this at many points on a grid, the slope field results that shows a family of solutions to the given differential equation. If also given a point on the function itself, then you can sketch the graph of a particular solution, even if the exact algebraic solution is not known. Since the computation of a slope field at any significant number of points is time-consuming, it's best done on a graphing calculator or computer, which I will show you how to do in class. How to create a slope field. Here's my derivative equation. It requires an x and a y. So I have an x and a y. I write my derivative equation, and at each given x and y, I can find my slopes. -2, -1, -2, 1, and so forth. So here are my slopes that correlate to here. Look at my scale. There's 2, so that makes this 1. Okay. We're going to use the slope field to sketch the solution that passes through the point 1, 1. So here's 1, here's 1, here's that point here, and we're going to go this way and this way. Remember, if we're concave up, our little tangent lines have to lie below it. So we're going to kind of skirt between these. And we'll do an example in a minute of making a slope field. So the slope field for the equation y prime equals x plus y is given here. Carefully sketch the solutions that pass through the points 0, 0, -3, 1, and -1, 0. So here is our figure. 0, 0, of course, would be this one. Okay, and we'll look at that. -3, 1, we're just approximating. This is -4, so probably that's about -2, and here's about -3. Here is 4, so that's probably about 2. This would probably be about 1, so -3, 1 is going to probably put our point about right there. And -1, 0. -1, 0. Oh, that one looks real easy. Look at that. That's going to be this line right there. So give it a shot. Pause the video and sketch those. Give it a shot. And here's what you should have gotten. Here is through 0, 0. Here is through -3, 1. And -1, 0. All right, you'll do the next one on your own. My slope field equation here only had x in it. Notice that the slopes only change with respect to x. Okay, so when I'm at x equals 0, I have the same slope all the way up. When I'm at x equals 1, I have the same slope all the way up. This slope field is one that is determined only by x. This slope field has the equation dy dx equals y. And notice it changes only as y changes. So for this y value, the same slope all the way across. Same slope all the way across. Notice this one has the equation dy dx equals x over y, so it changes as both x and y are changing. Look at the shapes that are happening. So we are going to sketch the slope field for dy dx equals x plus 1. Now, there's really not enough room here to work it all out on this page, so you might want to actually do the work on the previous page for the other problems. But we've got the point 0, 0. So dy dx when x equals 0 is 0 plus 1, which is 1. So when x is 0, my slope is 1. So I'm just going to envision that little slope, and all of the x equals zeros are going to have that slope. Okay. Now let's look at dy dx when x equals 1. Okay, so that would be 1 plus 1, which is 2. So when x is 1, I have a slope of 2. So I have to kind of imagine or envision sketching a slope of 2. Maybe I look at it like this, and I can get my slope to be a little steeper. And I don't want it that big. And all of them will have this slope. All of the x's when x is 1. I think I might have made those a little too big. Now what about when x equals -1? That's going to give me -1 plus 1. Ooh, that's 0. So when x is -1, my slopes are 0. So I'm going to have a bunch of horizontal lines. You can see what's beginning to develop here. What about dy dx when x is -2? That's -2 plus 1, which is -1. So again, going to envision a slope of -1 connecting with that point. What about when dy dx, when x equals -3, that would be -3 plus 1, which is -2. Again, imagine connecting those points, and these will all have the same slope because everything depends on x. All right? Okay, I can see when x is 2, 2 plus 1 is 3, so I have a steeper line than that. So steeper. When x is 3, it's going to be 3 plus 1, 4, even steeper than that. So there you go. You can see it doesn't really take very long. So your TPs for section 6.1, part 1, will be problems from the text, 49, and then 53 through 56 is a matching. And then the lecture manual, this page, you're going to do 2, 3, and 4. Then you're going to back up to page 90 and do number 2. And then you are going to read, and I do mean read. I've even underlined important things, pages 91 to 94. See you next time.